All right. Well, thanks everyone for attending my talk and particularly your interest in engineering education. I know the talks in this series are more focused on the research side of things, but I'm in a little bit of a unique position being the chair of the manufacturing program, but also in the educational leadership stream here at UBC Okanagan. I thought I'd mix it up a little bit and talk a little bit about the manufacturing program and kind of how we approach training of our students to be competitive in this Industry 4.0 era. um, so this is a quick outline of what I'll be talking about, just a little bit of an introduction and motivation as to why we're interested in Industry 4.0 and manufacturing in general when it comes to undergraduate education. I'll talk a little bit about the academic context and the lab facilities that we have here. And I'm going to do a bit of a deep dive into one of the courses that I think really is representative of our kind of teaching approach in the program. And then, as Bryn mentioned, we can have certainly as much time as you like for a discussion and questions, and also comments. I'd love to hear everyone's thoughts on what I'm presenting on today as well. So actually, I'm going to start with a little bit of an audience interaction, which is always a little bit scary. We'll find out who's truly listening here. But I actually start with this example in my classes, and I have 3 cars here. And my question, and you can put it in the chat or you can unmute yourself and chime in. But if you had to buy a new car and these are your 3 choices, what do you think your deciding factors would be, or what product do you choose and why? Addy says Toyota, okay, but why? I'm not asking which one. I'm asking why. Honda for reliability. Alon says the EV. Well, let's pretend they're all just old school combustion engines. Anything else? Fuel efficiency. Okay. And color. Emily says color. It's funny. I gave this talk at UVic a couple days ago, and that was the first one that came out as well. Yeah. So, and I'm surprised no one said priced, brand loyalty, but, price, I think, is a good reputation. But, I think the first thing that you should really notice about these 3 vehicles is they're basically the same thing, right? I mean, we have a Honda CRV, we have a Hyundai Santa Fe, and we have a Toyota RAV4. And it's really difficult to distinguish really these cars and to say why is one car is better than the other. But I think you hinted on a few of them. So price is one, reliability is another, brand reputation. But those are not properties of the product itself. These are actually properties of what I would argue is the process, the manufacturing process that is used to make these cars. And ultimately, the cost of these cars comes down to the efficiency of the manufacturing process. So that's kind of how I wanted to start this, was with a little bit of a claim that the economic efficiency of a company is rarely a property of its product, but rather the process that's being used. And that competition is really between processes. And even though customers don't judge isolated improvements in these processes, the capability of the entire process is what the customer judges. So you don't really care how efficient a certain assembly process is, but of course that all comes down to the bottom line that you end up looking at when making a decision. So this idea of process optimization and process efficiency is kind of what drives all of the industrial revolutions. If you look back to the first industrial revolution, where we had steam power, the second industrial revolution, which was mass production, and that's enabled by the availability of electricity. And then we have automation, which is again enabled by computers. And then now we're in what a lot of people are calling this fourth industrial revolution, which is all about improving process capability through the interconnectivity and digitization of our manufacturing processes. So it's really, this idea of process capability is really what's driving these revolutions. So why are we interested in making sure that we're providing students a great education to be competitive in this area? Well, the first is actually manufacturing, believe it or not, is a big deal in Canada. And That's actually a hard message to send to students. I think manufacturing has a stigma about it. It's a dirty, male-dominated environment, maybe old technology, but that's not at all what the current landscape in manufacturing is. And you can see that actually there's a huge job impact as well, right? We have 1.8 million jobs in manufacturing, in core manufacturing, but up to 3 million jobs kind of related to manufacturing within Canada. That's about 10 to 15% of the workforce in Canada. And this is old data as well. This is 2016. More recent data, actually, this is very recent, just came out in October by the Canadian Manufacturers and Exporters report on labor and skills surveys. Labor and skills survey report. And you can see that there is an increasing challenge that manufacturers are having in recruiting skilled labor and people with expertise that they need. So they've been tracking this since 2016, where 39% of manufacturers faced a labor or skill shortage. And then post-pandemic, we're up to 82%. And actually that trend started pre-pandemic as well. So of course the pandemic changed a lot of things, but this trend is unchanged. So obviously there's a need for us to graduate more students that are able to go into the manufacturing sector. This is again from the same report, which asked what government programs or policies would best help you address labor and skill shortages in the long and short term. And there's two, and maybe if I could get my pointer up, I can even highlight them a little bit. There's two that I really wanted to kind of highlight here. The first is provide more support to encourage automation. And that's actually really good news for universities. Because a lot of the skills shortage in manufacturing is more technical or technologist skills, maybe something that the like of BCIT would be providing. But this drive for more automation really means that we need engineers entering in manufacturing. The other one that I wanted to highlight is that people in industry want better alignment of the post-secondary curriculum with industry trends. And I'm going to talk a little bit more about that because that's a unique challenge I think we have in Industry 4.0. Again, a little bit more data and a very similar message. The two that I wanted to really highlight to you here is that companies are being prevented from investing in workforce training because this lack of satisfaction with the results of past training programs, meaning we've done these things before and employers aren't really seeing the value in it. And the other one, which is actually the bigger percentage here, is that no existing training programs fit the specific needs of a business. So, this implies that, to some extent, the education system is not doing a good job, and it's also not even really targeting the right thing. So again, these are some of the challenges that we're faced with. So, if I had to summarize some of the challenges from an educational perspective, the first is that there's this unprecedented adoption of new technologies, and we have these very short innovation cycles. And you talk to an advanced manufacturing company, and they're talking about the pace at which the industry is moving, and that's very difficult from an education perspective because we have to decide what we need to teach students in order to keep up with this dynamic and changing environment. We have aging workforce. So again, I think that has to do with young people are not as interested in manufacturing. There's also no consensus on Industry 4.0 skills because Industry 4.0, even the definition is still a little bit dynamic, and it's not clear exactly what skills students need in order to be competitive in Industry 4.0. Employer values are shifting from academic education to skills training. So I think sometimes employers are valuing the engineering skill set a little bit less than the technician's skill set. And then this last point is very similar to what the first point is, that there's just emergence of these new and specialized sectors that are very difficult to kind of keep up with at the university level. So I'm just looking at the time here, but this whole challenge is really why the manufacturing program was started at UBC, and it is a joint program between the two campuses. It's really the first and only joint engineering program that we have across both campuses. And I think it's a great model for how we can have more intercampus collaboration as well. We're focused a little bit on the undergraduate program at this point, but it's natural that that trickles into the research realm as well. So this is definitely something I'd like to see more of our engineering programs go towards, is this kind of cross-campus offering of programs. I don't want to go into a lot of the details here, but it is a brand new program, and we just got accredited last year, and our first cohort of graduates graduated last year. So, what do we teach in manufacturing? The green line in this radar chart kind of shows the focus areas of the program, and there's really three main areas. One is engineering management, which is supply chain management, life cycle analysis, production system management, some of those industrial engineering topics that are really not taught anywhere west of Ontario here in Canada. We also have a strong focus on intelligent systems and control, and also advanced manufacturing. So these are the lab facilities that we have for teaching Industry 4.0 skills. And these are basically lab scale production systems, which allow students to program the control system and interact with sensors and actuators that are typical of a assembly process or any kind of production line. So there's distributing parts, there's sorting parts, there's pick and place, there's quality assurance and quality checks. So all of these are very common functions that you would find in a production facility. And we purchased all of this equipment, or most of this equipment, from a company called Festo, which has a didactic side to the company, meaning that they're primarily an industrial automation company, but they provide these educational training systems to help students get hands-on experience learning Industry 4.0 concepts. I am going to focus on this right-hand system here, which was which we call the cyber physical lab. So I will go into a little bit more detail into that shortly. But one thing I did want to kind of mention is one of the reasons we went with this equipment is that it was strategically part of a certification program, which is a three-way partnership between Festo, a nonprofit called the National Coalition of Certification Centers, and UBC. And they have a three-level certification program that is basically stackable certificates that students can earn by the very means of us having this equipment and me being qualified to issue these certificates. So students are able to get these industry recognized certifications through the courses that we offer, but then it also enables the faculty and the school to offer these as micro credentials to industry folk as well. So we have run a couple of those where we've had people from we ran it during COVID, so actually we were able to run them virtually, and we had participants from all over the world. I had a plant manager from Nestle in Nigeria as one of my students, so it was very cool to have that kind of that broad reach. So of course COVID enabled a lot of that, but I just wanted to mention that this is part of the reason why we went with Festo for this equipment, was the certification program. So I'm actually going to jump over to, I have a quick video of our cyber physical lab in as it works, and I'm gonna hopefully the audio isn't super important. It's just kind of a soundtrack over top, but I will see if I can't get the audio to work as well. This is just a quick minute. It's going to show you how the cyber physical lab works and what it does. I guess I should tell you at first, it simulates the assembly of a cell phone. So it goes through a circular conveyor system, which is what you'll see, and it starts by dispensing a cover, and then it goes and completes the assembly of a simulated cell phone. So I'll maybe show you a little bit how we can use it directly from our own cell phones. So we can, for example, order a part from our cell phone, and once it's been added to the queue, as the pallets come to the stations, you'll see that the process is started. Hopefully that came through okay. I know it's a little bit choppy over Zoom. It's never ideal, but hopefully you got the idea. All right. So yeah, basically it does this simulated cell phone assembly. You know, it's a modular system. So each of these stations has a base conveyor module within an application module that sits on top. And the application module is what's different for every station. And each of those applications here is kind of outlined on this slide. And you, hopefully you're able to follow along with it, but there's a front cover which is dispensed onto a pallet system. There's a quality check to make sure that that cover is correctly oriented on the pallet. There's a simulated drilling or a machining operation. There's a manual pick by lights station where the operator is cued by lights on what parts to actually put into the cell phone. There's a back cover dispenser, a press which joins the two covers, a labeling station which puts a QR code and order information on the cell phone, and then finally an output station that sorts between, you know, good product versus bad products or defective products. For those of you who are interested in the control side of things, this is the control hardware that's used on the system. So we have PLCs that are controlling each of these stations, Siemens PLCs, but then we also have a master slave system with some of the Festo PLCs. And then we also have an MES, a manufacturing execution system, which runs to operate or to basically coordinate the entire thing. And the MES, or the manufacturing execution system, is really what I have students focus on in this course. And basically they reconstruct the manufacturing execution system. And this is really, the manufacturing execution system was basically, you know, it takes a customer order and it creates a work plan and executes it on the overall system. And so everything is done without a human in the loop. And that's what I would argue is really what's allowing the improvements of in terms of process capability here is this manufacturing execution system. So the course that I use this in is called Factory Planning, and it focuses on this factory scale automation. And, you know, if for those of you who are familiar with the automation pyramid, it really focuses on this planning level or the manufacturing execution system level of the automation pyramid. And kind of the unique way that I run the course is I show the students the cyber-physical lab system working, as you saw in the video, in the first lab. And then the second lab, I completely delete the entire control system. So it's just empty PLCs, empty computer in the room, nothing's working. And I say, make it work by December. You know, before you go for Christmas break, I want this thing operating like you saw in the video in the first lab. And it's a daunting thing, right? But it's really realistic. I mean, I worked in industry for a while, and that's exactly the type of problem that we would have to solve. You know, we'd be given a system as a controls engineer, and we'd be told, make it work, right? And so that was kind of the intention behind this this approach for using the system. And I know I only have a couple minutes left, so I am going to skip to this last slide here, which I think kind of hammers home the point that I'm trying to make, which is how do we train students for this dynamic environment where there's these short innovation cycles? And the answer, some of you might not like, is actually to look at what accreditation or engineering accreditation asks of us as an engineering program, which is to really focus on the attributes that our students are getting out of this course. So I don't, at the end of the day, I don't care if a student can program a Siemens PLC or if they can control a Festo PLC. What I really care is, do they have those design attributes? Do they know how to use modern tools? And this isn't a specific tool. I just mean, if they had to pick up a tool, would they be able to figure out how to use it by using documentation, experimentation, and adaptation of these tools? Communication, I really emphasize good engineering documentation. Lifelong learning, engagement in the lecture, and individual and teamwork, because they have to work as a team on this, because it's a system level approach to teaching, and you can't do a systems level project without working very closely with other team members and other groups as well. So that's kind of, if I know I'm out of time here, Bryn, so I do want to wrap it up, but the thesis of my talk here is really focusing on those graduate attributes as opposed to specific skills that are maybe tied to a particular technology. And you talk to industry people, they'll give you the exact same message. They'll say, we want students who have great communication, can work well on a team, have design thinking skills, and can pick up something new and figure out how to use it and apply it very quickly. So that's, and I'm going to do one shameless plug here. For those of you who are interested in engineering education, we are hosting the Canadian Engineering Education Association conference here in Kelowna in the summer of 2023. 500-word abstracts are due by November 28th. Love for you to come, meet other people who are doing engineering education across the country. And feel free to come and see our labs as well, and talk to me about it. So with that, I will be quiet and take any questions, comments, suggestions, critiques. Thank you.
Fantastic. Thank you so much for the great presentation, Dean. Certainly a fascinating topic and very prescient in the world we're currently in today. Okay, so we now have 5 minutes for questions from the audience. Feel free to raise your hand and then unmute yourself, or you can type your question into the chat.
Hi, boss.
Hi, Dean. Thanks for the great presentation. Definitely very cutting-edge area, and I'm glad to see that you're leading this here at UBC on the educational side. So one question I keep receiving from students and as well as industry employees, that these cyber physical factories, on one hand, yeah, it's great coming towards the emerging digitization, automation, and we are educating the students here to integrate to such industries. But on the other hand, inherently, by the nature of the topic, it's going to reduce maybe the number of jobs. The video you were showing, we don't need as much as manual work anymore. Everything is automated. So I'm just wondering, how would you answer that? How you marry these two?
So, I think the answer that probably you hear all the time is, we'll have more automation jobs, which is true to some extent. I would answer this in two other ways, though. One is, we simply are having less people in the labor market. That's for sure. So we actually need to automate, because we won't be able to fill the current job need with people who are coming into the job market right now. There just simply aren't enough people in the world to do everything we need to. So we need to adopt automation in order to keep these cutting edge things going. The other is that, I see automation as really being an improvement of jobs, right? So, automation is really about taking away the jobs that don't need to be done by humans because they're dirty, they're, they are physically demanding, they're boring, right? So there's, I think there's a real good case for adopting automation to basically making work more enjoyable for people and less dangerous.
Yeah.
I see a question in the chat there from Madison. Is the certification program available for mechanical engineering students at UBCO? The answer is yes, if you're in the mechatronics option. then you take some of my courses through that, and you can earn the certification through that.
Fantastic. Any other questions?
Maybe I have one more. If industries are interested to use this facility that you showed for research projects, is it open or no? It's purely for educational purposes.
Good question. I think historically there's been this hesitation to mingle educational lab equipment with research. Talk to me. I think that we could probably arrange something. One thing that I would argue, I think this is great for training purposes. I'm not sure how good it is for research purposes, to be honest. So I would probably want to sit down with whoever would be interested and see if we can't find a better research platform for what they want to do. Yeah.
Thank you.
Yeah. Emily?
It wasn't really a question. I just wanted to say thanks, Dean. I thought that was really interesting. And I don't know if you know Jonathan Verrett in chemical and biological engineering, but him and I talk a lot. I used to teach a course on, so he's in engineering leadership, which is why I mentioned him. I used to teach a course on problem solving, and it was very much about like breaking down skills needed and sort of teaching them outside of the context. And so I think it'd be really interesting to sit down with you and talk about some of those individual skills, things like analysis and classification and divergent convergent thinking, time management, team building, and how you sort of develop a language around problem solving, because I would love your input on which parts of what we're doing is maybe a little bit too archaic and doesn't fit within some of the types of projects and courses that you're talking about now. Because I do have plans now to teach a similar course in the upcoming years, and it would be nice to maybe get rid of things if you're like, oh yeah, no one's going to need that skill anymore. Maybe we could brainstorm a little bit together. So I thought it was really interesting, and it's not a question, just a comment.
Okay, yeah, thanks, Emily. And yeah, I know Jonathan, and I'd love to sit down with the two of you and talk more about it. Yeah,
it could be fun. Thanks.
And actually, I saw in the ad for this, you were listed as UBC Okanagan.
Yeah, no, I'm not.
And I got really excited. I thought, oh, Emily's coming to UBCO, and then I realized, oh yeah, you're still there. So
yeah,
yeah,
I'm like quarantined in my house right now too because I'm sick. So I am definitely not anywhere other than downtown Vancouver. Yeah.
Okay. Yeah. No. Thanks for the comment. I'd love to chat more about it.
Thanks.
Fantastic. So I think in the interest of time, we'll wrap up this Q&A and we'll move on to our second presentation by Dr. Emily Cranston. So just to give Emily a brief introduction, she's an associate professor in wood science and chemical and biological engineering at UBC's Vancouver campus and is the president's excellence chair in forest bioproducts. Prior to January 2019, she was an associate professor at McMaster University and the Canada Research Chair in bio-based nanomaterials. Emily's academic path began at McGill University, where she received her honors BSc in chemistry with bioorganic specialty and a PhD in materials chemistry. The study of value-added products from cellulose took her to Stockholm, Sweden, as a postdoctoral researcher at KTH Royal Institute of Technology before she returned to Canada in 2011. Emily received the 2017 KING-FA Young Investigators Award for the American Chemical Society Cellulose and Renewable Materials Division, the 2018 Kavli Foundation Emerging Leader in Chemistry Leadership, the 2021 TAPI Nanotechnology Division Technical Award, the 2021 Lasser Award from SCI Canada, and currently holds an EWR Stacey Memorial Fellowship from NSERC. So as with the previous presentation, Dr. Cranston will give a 20-minute presentation followed by a 5-minute Q&A. And once again, Jolene will ring a bell to indicate end of time when that rolls around. So I'll pass the floor to you, Dr. Cranston.
Perfect. Thanks a lot, Bryn. Can you see my screen and hear me? Everything's okay?
Yep, all good.
Perfect. For those that might not have heard me whining at the beginning, I've been out sick for about a week with some daycare germs that my son brought home. So please excuse any coughing or sniffling. My voice is normally a little bit nasal, but it's extra nasal today. So please bear with me. I really appreciate the introduction and the opportunity to talk to you today. So thanks for coming. It's always my great pleasure to share with you ongoing work in my Sustainable Nanobiocomposites group, which is at UBC Vancouver campus. And I am jointly appointed in wood science in the Faculty of Forestry and also in chemical and biological engineering in applied science. And as Bryn mentioned, I hold the President's Excellence Chair in Forest Bioproducts. So my research really focuses on nanocellulose, and I'll get into an introduction of what that really means. But the idea is, can we tailor surfaces or through interfacial engineering, can we really lead to some new sustainable bioproducts? So that's our goal there. So I hope that when I say nanocellulose, you all have some idea what I might be talking about. The question could come up, does this mean we just grow really tiny trees? And the answer is no, we don't grow really small trees or plants, but we isolate or extract nanocellulose from natural cellulose sources. And in BC and in most of the world, we tend to think about wood pulp and trees when we talk about cellulose, but it's important to know that we can also get cellulose from other materials. So things like algae and bacteria and fungi, and also some animals like the sea tunicate, which is shown here on the right. So these are all very interesting and diverse sources of cellulose. And what we do is we take a top-down approach to nanotechnology, meaning that we're extracting something. In this case, nature has already synthesized it and built it for us. We're just breaking down cellulose that's natural into small crystals or small fibers. And then we add surface charge so that they form stable colloidal suspensions in water. And what this means in more simple terms is that from a sustainability or a green perspective, we're just working in water and we're not working with solvents, but also stability means we have predictable performance and predictable processing of materials. So this is the overall idea of nanocellulose. If we want to look at it in pictures again, and we take the tree as our most typical, most common starting material, we can break the tree down into pulp fibers. And then from pulp fibers, we can either go mechanical methods to produce cellulose nanofibrils or chemical methods to produce cellulose nanocrystals. And the cellulose nanocrystals are sort of rigid whisker-like particles, and they're the ones that I'm going to focus on for today's presentation. But you can think of these materials more as being like an uncooked basmati rice in terms of rigidity and aspect ratio, whereas the cellulose nanofibrils are a little bit more spaghetti-like, cooked spaghetti-like. So you've got rigid and amorphous, crystalline and amorphous regions, and that means that those materials tend to entangle a little bit more. So whereas the spaghetti material might be better for gels and reinforcing, or gels and rheological modification, our cellulose nanocrystals are a little bit better for creating percolated networks and reinforcing plastics, for example. What I should mention is that these materials really aren't new, and they were isolated and identified in some cases as early as the 1950s. But the real push towards sustainable materials and also refreshing the forest industry in Canada has led to the recent renewal in this research area. So in my group, we are interested in these materials, both the spaghetti and the rice-like form of nanocellulose, and using them in composites, in films and coatings, to study their self-assembly and liquid crystalline properties. Then we like to use them in gels and foams and emulsions, but also just as model systems to better understand cellulose-cellulose and cellulose-polymer interactions, which are really important in a number of different industries. And we have a really long list of potential applications, but most of these are still potential, and that's an important thing to point out, is that we think we can do a lot with them, but there's still a lot of science to be discovered on that path. And so I'll talk about some of these application areas in my short presentation. So for those that are curious, here I have a transmission electron microscopy image showing these whisker-like or rod-shaped cellulose nanocrystals. They're a few hundred nanometers long and a few nanometers in cross-section. Again, they're rod-shaped, they're strong, they're stiff, they're highly crystalline. They're obviously bio-based because we isolate them from cellulose, and they're non-toxic and biodegradable. For an organic, natural material, we have something that is very chemically, colloidally, and thermally stable and can be processed at temperatures upwards of 250 to 300 degrees, which is pretty impressive for natural materials. Our cellulose nanocrystals have both hydrophobic and hydrophilic properties, which is interesting for stabilizing interfaces. And then one place where they really stand out compared to other nanomaterials is that they can be dried by different processes and then redispersed back in water. So you can put them in water and shake them up by hand and get something that's nice, stable, predictable. And that's really, really quite unique compared to other nanomaterials that once you dry them, they're then aggregated and they're no longer nano. You lose all the advantages of that extremely high surface area to volume ratio. And then one last cool property about cellulose nanocrystals is we can use magnets and electric fields to align them and control them. I'll give you an example of where we use that property in a few minutes. Another thing that we can do, so I showed dispersed in water, concentrated to form a gel, or dried to form a powder or a fluff. But if we dry these materials slowly and under controlled conditions, we actually get bright iridescent colors. And so these are structural colored pigments, but they're the kinds of pigments that would never fade because they're not actually based on dyes. And this could be quite interesting either in optical elements or security features, or maybe even just as, you know, decorative coatings or in cosmetics. So if we talk a little bit more, I mean, I think we all know cellulose and wood is a pretty good material and it's used ubiquitously in everyday life. But what's the advantage of isolating these small bits of cellulose? And I would highlight the three main advantages as the idea that when we do isolate them, we get these high aspect ratio particles, so these whisker-shaped particles, and that means you only really need a really small amount to greatly affect the surrounding material, or a little goes a long way. Because of how we isolate them, we remove all the weak cellulose and keep the strong stuff, and that means we have an ideal reinforcing component. And then lastly, because of this amphiphilic character, we have a nanoparticle that's really good at stabilizing interfaces and also good at dispersing other not colloidally stable nanoparticles. So we can use them in foams and gels and emulsions and suspensions. And so, as I mentioned, nanocellulose and the study of it is not that new, but it is something that has really picked up in the last decade across Canada. So I just want to show all these smiling faces of people that are very interested and have research programs heavily focused on nanocellulose. It is not just me, and particularly here on the West Coast, we have a great team. I did my PhD with Derek Gray, who's down here at McGill University, and he is really sort of considered the grandfather. So all of the work on cellulose nanocrystals came from his research group originally. And there's lots of science and there's lots of room for us all to be working on this. But one reason that you have such interest in Canada is because the pioneering work was done here, but also because that led to a lot of industrial production of nanocellulose. So we consider this an emerging nanomaterial or emerging commercial nanomaterial, where we know that multiple suppliers is going to be really important for the market growth and ultimately the success of the material. So across Canada, really from New Brunswick over to Vancouver, almost full coast to coast, we've got a number of different companies producing different kinds of nanocellulose and at different capacities and using different processes. And so there's really quite a lot of interest going on, but then there's also, you know, industrial funding for all those researchers I showed on the last slide. So this is really important for Canada. We're definitely leading the way in terms of the industrial production and the research related to nanocellulose. It's an exciting place to be. So my research program aims to bridge the gap between these industrial producers of nanocellulose and potential end users of the new technology. And we hope that by exploring the fundamentals that we'll be able to show the importance of discovery-based research, and that the new science and technology will ultimately lead to new commercial products, new sustainable materials with a strong Canadian footprint. And so Some of the things that we've done with cellulose nanocrystals and where we've led the field include being the first to use cellulose nanocrystals in supercapacitors, so in energy storage devices, where they played a structural role in making up the electrode. We've developed new mechanical testing methods in order to evaluate nanomaterials, which can be really challenging. And we've done all of the benchmarking that's available in the literature to date on the commercially available nanocelluloses. We've looked at quantifying how we can use magnets to align nanocellulose and how we can control the material that way. And we've contributed to some reviews on hydrogels. So water-based gel materials that are often used in cosmetic and pharmaceutical applications, but also dry aerogels and foam-like materials, and also in emulsions. And so emulsions and latex systems are really important in a range of commercial products, as well as separation processes used industrially. So everything in my group sort of falls into one of these categories. Either we're breaking down biomass, we're modifying the surface chemistry, or we're building up interesting new structures. But our hope is really that by controlling and understanding particle chemistry and the interactions more at a molecular level, that we can link that to functionality and ultimate performance of these materials. And that by doing so, we're developing design rules which are applicable in many different areas and to many different kinds of bioproducts. And so just to give you a few examples in three categories, we work in biomedical research, both with nanocellulose in terms of materials, but also processing. So we do a lot of spray drying in the lab, which is interesting, particularly in vaccine development right now, but I won't talk about that today. When it comes to nanocellulose, we have used nanocellulose to build up directional scaffolds. So again, using a magnet to align the cellulose nanocrystals and then showing that we could get muscle cells to grow in the direction of the nanoparticles. And by doing that, we can improve muscle regeneration and muscle growth. We could take a similar material, which was basically like a sponge or a foam, so a really flexible material that was entirely made out of cellulose nanocrystals that had been cross-linked together in a porous structure, and we could implant them into bone defects and show that bone would grow back 50% faster than if you just had a hole in the bone needed to span it, but instead it had a nice, flexible, biocompatible scaffold that promoted bone regeneration. And then another area that is linked to biomedical applications is looking at the production of porous microparticles, which might have use, to replace microbeads in cosmetics and household products, but also have the potential to be really high surface area absorbents, maybe for environmental remediation or as controlled release materials for pharmaceuticals. So that's just a snapshot of a few things in the biomedical arena. We talk a lot about food and cosmetics, since these are basically food grade materials, and a lot of cellulosics, particularly non-ionic cellulose ethers, are already used by Dow and DuPont in a huge number of food products. And so emulsions, oil droplets, or one liquid being dispersed in the other, are everywhere in food products, particularly. And so we talk about the idea of Pickering emulsions, where you use these nanocellulose particles to stabilize an oil-water interface or an oil droplet in water. And what we found is that if we control cellulose nanocrystals with co-stabilizers, that we can get extremely stable emulsions. And in fact, these emulsions, and this is what an emulsion looks like once you've sonicated it, so it's one phase dispersed in the other, but it looks completely uniform. And what we want it to do is stay looking like this for a really long time. And so what we've shown is that we can make really stable emulsions, and the droplet size is very, very small, which also lends itself to stability to coalescence. But by changing the amount of co-stabilizer that we add with the cellulose, we can go from having an oil and water emulsion. So here the oil phase is dyed green, and we can flip it to have a water and oil emulsion. So we can really tailor the properties of an emulsion and control its stability to a much greater extent than you can do with small molecule stabilizers. So the interesting thing about being able to make really stable emulsions is that we actually could dry them completely. And that meant that we're left with a white oil powder that looks like a dry material, but is actually 95% liquid oil. And so this is really interesting from a transportation perspective, since so many commercial products are emulsions, that if people could dry them, just ship the valuable component, and then on the other end, the customer or the people selling the product could put it back in water and shake it up by hand. This would avoid transporting water around the world, and from a sustainability perspective as well as a cost perspective, that's really important. But it also opens up sort of a new encapsulation method, a new way of protecting materials, maybe agricultural oils that aren't very stable and that oxidize easily, like corn oil, like oat oil. We can work on that. And then we can also look at interesting pharmaceutical and cosmetic scents, flavors, and that the ability to encapsulate them inside a very, very thin but robust and stable cellulosic shell. So we've been having a lot of fun making these powders through freeze drying, spray drying, and spray freeze drying in order to tailor the properties, the encapsulation, and the controlled release of different oil-based components. And these are entirely plant-based capsules, essentially. And then the third category and the last category is more looking at latex polymers, composites, and adhesives. And so when I talk about latexes, I mean synthetic latexes where we have polymer spheres that are stably dispersed in a water phase. And so what we have shown is that when we add cellulose nanocrystals into latex polymerization, we can really control the role of the nanoparticles and therefore affect the polymers that are synthesized. So for example, we can make fairly big polymer microspheres where the cellulose nanocrystals form a layer at the interface, or we can make latexes where the CNCs are just sort of playing a passive role and they hang out in the water phase, and the particles of the polymer themselves are stabilized by a surfactant, and then we get much smaller particles in the 100 nanometer range. Or we can even get particles with dual morphology where they have big particles, but they have small particles attached on the surface, and that's by changing the ratio of cellulose nanocrystal to the co-stabilizer, which in this case was methyl cellulose, another food grade polymer additive. And so being able to control this size and shape and roughness is pretty important when we talk about latexes that are often used in things like inks and toners, as well as rubber, and where the friction and how the particles move past each other is really important. And then an ongoing project with the University of Ottawa and Queen's University as well has been scaling up the latex synthesis to produce water-based pressure-sensitive adhesives. And when we talk about making adhesives, they're normally made by very energy-intensive and solvent-intensive processes, but here we're moving to all water-based, so much greener synthetic protocols. And then we're improving the adhesives by adding nanocellulose. And what you normally see in adhesives when you add in any kind of modifier or any kind of additive is that if you improve adhesive properties, you decrease the cohesive properties. And these two things always fight each other. But when we use cellulose nanocrystals, we have this simultaneous improvement in all of the performance metrics. So everything improves. The cohesive strength or the shear strength and how the latex, the sticky part itself holds together is much, much better. It improves like 35-fold, but the adhesive properties also go up almost 10-fold, meaning that how it sticks to an opposing surface is much better. So we've been working really hard to better understand the mechanism and why adding cellulose nanocrystals actually improves all of these performance metrics. So those are some of the things that I'm most excited about now. I hope that in the short overview that I've shown you that nanocellulose is a promising and sustainable and emerging commercial nanomaterial. This is a pretty multidisciplinary and exciting field. And I think we really are working towards very interesting tailorable materials with applications across a huge range of areas. And so hopefully, really leading towards more sustainable and greener bioproducts and devices, as well as greener processing. And so with that, I want to thank my collaborators in my group, and to thank all of you for your attention. I'm happy to answer any questions.
Thank you very much, Emily. And yeah, with that, we can open the floor to a couple of minutes of questions.
Thanks, Emily.
Thanks.
Great presentation. Great to see you, and hope you will recover very soon.
Thank you.
One general question again for our industry audience. What are the main obstacles that you see to upscale these processes from the lab to industrial products? I know it's not completely there yet, but I want to hear from you.
Yeah, no, those are great questions. And I showed you that we've got all those commercial producers in Canada. So they're all doing a really good job, and some are even up to 1 to 2 tons per day production capacity, where the major improvements from what we do in the lab have been in the separations and purification. So those end steps before you have a pure nanomaterial. Companies are working hard to take the byproducts of these reactions, which is basically just sugar that's been degraded, and ferment it for biofuel production, so that there are no losses, and so that we don't just flush the glucose or the broken down polysaccharides away. The main ways that cellulose nanocrystals are produced is using sulfuric acid. And so then there are companies that are looking at oxidative methods or using hydrogen peroxide, where the only byproduct is water, and sort of moving towards more sustainable practices. But I wouldn't say that there aren't that many bottlenecks in the production. There are ways we can make it more carbon neutral. There are ways we can make it more sustainable, and ways we can use less harsh solvents. But the companies are doing a great job. Where the bottlenecks is now getting these high quality, well characterized materials into end applications. And there, obviously, for this audience, things like thermoplastic composites reinforced with nanocellulose would sound like a really good area to go, but that's been one of the most challenging ones because of the incompatibility between cellulose and hydrophobic polymers. So there, people are looking at all sorts of ways to modify the surface of cellulose nanocrystals in order to make them more compatible. And then that starts adding a whole bunch of steps and cost and energy. So I think that we're still a fair distance from really good ways to get these materials as reinforcers in nanocomposite type applications. But the ones that I talked about today are almost all water-based. So it's taking advantage of nanocellulose, the way it's made, not needing to change the surface chemistry, and working in water where we understand its behavior. So we're sort of in a let's start with the low-hanging fruit first, which is mostly water-based systems. And hopefully, once we get those products out there, start spending a little bit more time on the development of industrially feasible surface modification routes to get to the harder products, which might be, working in solvents or working in hydrophobic polymers. But I can say that Schlumberger, which is one of the world's largest oil and gas technology companies, they use nanocellulose in water in about 10 different kinds of industrial fluids that all need different kinds of properties in terms of density and rheological properties and whatnot. So there really are large scale, large volume applications out there, but they're not necessarily as, they're not, the product isn't as obvious as some of the ones I talked about it just in my examples.
Thank you very much.
Does that answer your question? I think you had a few things in
timing
there.
and yeah, for partnership with industries. Thank you.
Yeah. No, Canada's doing really, really well.
Fantastic. Then I think in the interest of time, we'll have to close out this Q&A section, and we'll just move on to Jolene's Wheel of Fortune to award the gift card for today. So Jolene, if you could share your screen and run that, that would be fantastic.
Okay, here we go. Let's see if this works. Can you guys see that? No?
Okay, give her a spin. Yep.
Oh, you can see it. Okay, perfect.
Yep.
Okay, here we go. Okay, Yurkin Tulanov.
Fantastic. We'll
So I will-
be in
We'll be
email
in touch.
contact.
Yeah, we'll be in touch. I'll email you to award you that gift card. Thank you very much for attending.
Okay, fantastic. Thank you so much, everyone, for coming today. It's been a great session. Thank you very much to the presenters, Dean and Emily. Those were fantastic. And we'll be sending out possible invites in 2023 for future Café series. So keep an eye on your inboxes for those. Thank you, everyone, and have a great rest of your day.
Thanks, everyone.